everyone, I'm Yinzi. So I don't work on the three-body problem or planet habitability, so I'm an expert in neither. But for today, I thought I would just go over some of the basic physical principles that show up in, for example, science fiction. I don't know, has anyone read or seen either the books or the TV show? Yeah, so I basically just wanted to talk about the premise of science fiction because I do enjoy science fiction. So part of the plot of these stories is that there is an alien species who came to Earth from another solar system. And they're called the Trisolarians because their solar system has 3 stars in it. How do I move this forward? Oh, okay, there we go. Yeah, so the Trisolarians come from a system that has 3 stars in it, and then their planet is also somewhere in that system. And I want to talk a little bit about what it might be like to live in such a system. So first, one thing I want to go over is what sets a planet's temperature. So here on Earth, it kind of varies depending on where you are, but overall there's like a small range over which the Earth's temperature can vary. Okay, so imagine you have some light coming from your sun, and your planet is just catching that light from the sun. And if you do a simple geometric calculation, you can show that the amount of light you capture from the sun roughly, if for the same size planet, roughly goes as 1 over the distance squared. And so here, if planet B is twice as far as planet A, it will receive roughly 1/4 of the light. And then if you assume that the planets are in thermal equilibrium, as in all of the energy that they absorb from that star gets then re-emitted, what you can do is calculate what that temperature would be. So just using some simple proportionality constants, what you find that, roughly speaking, the temperature of a planet will scale about as 1 over the square root of the distance from that star. And so, for example, here, I've moved planets A and B around so that now planet B is 4 times as far away from the star as planet A. And this means that using this proportionality scaling, if planet A has a temperature of 300 Kelvin, it means that planet B will have a temperature of about half that, so 150 Kelvin. If you convert that to Celsius, which most of you are used to, I'm actually not used to Fahrenheit because I'm American, but if you convert that to Celsius, you get the difference of about from 27 degrees Celsius, which is nice and kind of comfortable, maybe a little toasty. But planet B will be minus 123. So you definitely don't want to live on planet B if you're a human, because that's bad. You'll freeze. So yeah, what we kind of call the habitable zone is the range where liquid water will exist on the surface of the planet. And it's possible that some forms of life don't need liquid water, but at least for Earth-based life, it's really important. And so when you hear exoplanetarians talk about the habitable zone, what they mean is basically the range over which you can have liquid water on the surface. So temperatures from 0 Celsius to 100 Celsius. And if you look at what the solar system looks like, what that habitable zone ends up being is kind of the range. It'll include Venus, Earth, and Mars. So obviously, at least as far as we can tell, there's no life on Venus or Mars. So just being in the habitable zone isn't like the only condition. But that's just kind of roughly how it's defined. Okay, so now we're going to talk a little bit about orbits. If you just have 2 bodies of mass, they'll pretty much just orbit each other forever. It's a very stable configuration. And if you toss a planet into that system with 2 stars in it, it's not really going to change what the stars are doing because the mass is so tiny relative to the stars, it doesn't really perturb them very much. And so there are some certain stable configurations. So you could have a planet going around both of the stars, for example, or you could have a planet go around one of the stars and then that whole system go around the second star. So these are both pretty stable configurations. There are some places where the planet won't be very happy, like if you try to put it really close. The stars will just keep doing whatever they want, but the planet will kind of get moved around a bit and it won't really be super stable. So yeah, that's just kind of like intuitively how you might think about what is a stable orbit for a planet and what isn't. So what the three-body problem refers to is that when you actually have three masses and they're like all kind of about the same mass, maybe a little bit different, this is a really hard problem to solve. There's no analytical solution for what they do, actually. What you can do is you can put it into a computer and try to calculate what they do step by step. So you will freeze the system, calculate what the gravitational influence of these three stars are on each other, and then move it by one time step further. And you can continue to do this to get numerical trajectories. And I'm not going to call them orbits anymore, because if you actually put it into a computer, the red, white, and blue curves are example trajectories for what the stars might do over time. And you can see that they don't look like orbits at all. And I'm taking a lot of figures from this website that I found, which is actually pretty cool. There's some cool visualizations if you're like an astronomer, like also a tutorial. So I recommend checking that out. It's pretty cool. So yeah, the stars are just kind of going crazy. And you can imagine that if you also throw a planet into that system, it's also not going to be very happy. So it might just get like shot all over the place. Sometimes it'll be very close to the star, sometimes it'll be very far away, and so its temperature is going to be very unstable. And that's why the Trisolarians, like their civilization kept on rising and then dying, because they would like all get burnt to a crisp, and then they would like all freeze to death. And they couldn't predict it, and so that's why they were like, okay, we have to find somewhere else where we can survive. And another thing that's interesting is that, okay, so let's say you know perfectly what your system is, and you can use this numerical simulations to predict what it will do in the future, but unfortunately, the trajectories depend wildly on the initial conditions. So the tiniest error in how well you think you know your system will lead to wildly different predictions for where it will be in the future. So the red and blue here are tracks for the same object in the previous figure I showed you. So these are for the same object, but if the mass of the object was changed by this like really tiny percent. So yeah, not only are the trajectories really crazy, they're also pretty much impossible to predict. And another thing that's actually kind of interesting is that I think the level to which they are hard to predict is also hard to predict, so you actually don't know like how far off you will be. So yeah, I guess I wanted to come back to the original question of, is it possible for life to develop in a triple star system? So the reason given in the books, and I guess the TV shows, I've only read the books, sorry. So the reason given in the books that they have this civilization rise is that there were long periods of relative stability in between the more chaotic periods, And so they would basically be able to develop life multiple times during these stable periods, but then as soon as you got like one of those crazy periods, then they would all die out. So that's kind of what happens in the books. I also wanted to say that not all triple star systems are crazy, because some of them might be hierarchical. So I showed the system on that side earlier, where you have an orbit that's of a planet going around two stars. What you can also imagine is that instead of that planet there, you replace it with another star. So you have a third star going around kind of outside of two inner stars, and then if you have a planet just around the outer one, that's probably fine. Because this system here is treating those two as like a single system. So yeah, you could have something that we call hierarchical, so it's kind of orbits within orbits. And then this is actually something I learned while trying to put together this talk. Apparently there are special periodic solutions to the three-body problem. And so this is actually a really cool GIF that I found on Wikipedia. And it's really fascinating to look at. I just like stare at this so long time. Yeah, but what I learned is that a lot of these are unstable, which means if you bump something by a tiny bit, it'll no longer follow that trajectory anymore. And even the ones that are technically stable, so you can perturb it a little bit, they're kind of improbable. So like the range over which they are stable is not very big. So you can move it a little bit and it'll come back, but if you move it by more than a little bit, it will become unstable again. Yeah. So to summarize, we think that exoplanet orbits are much likelier to be stable in single and binary star system, and this is something that you can check if you do numerical simulations. So as far as like when we're looking for exoplanets, we think there's a much higher probability that the planets around single and binary star systems are still around for us to like look at. And because looking for exoplanets requires precious telescope time, when we do look for things with telescopes, we tend to focus on single and sometimes binary star systems. And another like more logistical reason is that when you're trying to directly capture the light from a planet, you actually have to block out the star, or else the star will be too bright and you won't be able to see the planet. And it's like, so you can build instruments that block out the light of one star and look for planets around it, but it becomes a lot more complicated if you have to block out multiple stars. And so there's also a sort of technical reason. But yeah, that kind of looking for exoplanets, I think, is the topic of the next talk. So I won't get into that too much. So the takeaway from this talk is that, yes, it's probably possible for planets and life to exist in a triple system. There's nothing that makes it like impossible, but because it requires very specific conditions, and it's just generally a lot less probable, so we tend not to live there. So yeah, thank you for listening. I hope that's somewhat interesting to all of you.
Thank you very much. Do we have questions for Yinzi?
Yeah, have we actually ever found the planet that has three stars?
You know, I'm not sure. I am not sure, actually. So the question was how we found a planet in a triple star system. I actually don't know. So,
Sit back.
What percentage of these systems are triple star systems versus single or double?
oh, do you mean like the multiplicity of stars in general? Like how many systems out there have one star versus two star? So we think the majority of stars are actually binaries, and so most, I think like 50% or more, someone else can correct me if I'm wrong, but most systems I think are binaries. Yeah. And then I think single stars are more prevalent than triple stars.
Yep, up on the balcony.
These systems where you have periods of relative stability and then followed by a period of chaotic behavior, do they actually exist in real life?
Yeah, I think they can, but like it's all chaotic. It's just like sometimes you spuriously get things going around like for a while, yeah.
Yep.
Yeah. Do we know why these systems are so sensitive to initial conditions, or do we just know that it is?
Yeah, so why they are sensitive. So the question was, do we know why they're sensitive to initial conditions?
Yeah, so sensitive.
Yeah, so it's like basically a general, it's basically like sensitivity to initial conditions is just like what we call chaos. So it's basically like when you solve the system of equations, so when you solve the mathematical equations that govern the evolution of these systems, when you just like change one of them by a little bit and trace it, it just ends up being wildly different. Yeah, I think it's just because there's, yeah, it's just like comes out of the numerical calculation, I think. I don't know if there's a deeper reason. So if you have like a double pendulum, it exhibits the same behavior, and like weather is like this as well, if you've heard of like the butterfly effect. Yeah, it's just sensitivity to initial conditions.
Yeah. I was wondering, just how many of the systems are actually like sensitive to initial conditions? Is it just these three-body systems, or is it like more?
Sorry, can you repeat the question
How
louder?
many systems are actually like sensitive to these initial conditions? Is it just these triple body systems, or is it like more?
I think 3 or more. Yeah, I think 2 is, well, yes, two is perfectly solved. But with 3 or more, it's generically going to be chaotic. And as for like real life, there's a lot of things that are very chaotic. Yeah, the weather, especially like if you go, like some places, it's much harder to predict what the weather will be like down the line, and those are more chaotic, weather patterns. Yeah, so lots of things in real life are chaotic.
Do we know why the probability of forming a binary is so high?
Not my field of expertise. I think I'll have to talk to someone who works on stellar formation for that. So stars form from a collapse of a molecular cloud, and I don't know why it's more probable that they'll end up as a binary than anything else, but I don't know, maybe someone else in this group will have a better answer to that.
In your simulations, how often does it happen that they collide when you have a very chaotic track?
Yeah, so that's something that can happen. You can have things collide. I don't know, is there an analytical estimate of how frequently things will collide? I'm not sure if it was one.
I was thinking maybe from simulations you could maybe get a sense of it.
Yeah, like I said, this is not my field of expertise, but I think you could probably try a few numerically and see what happens. It depends. Then it depends on how big they are, and so then it depends on the composition, roughly, if it's, and then it depends on what collides means. Is it just they get close enough and tidally disrupt each other, so they rip each other apart, or do they mean physically the core goes through the core? So yeah, I think you'd have to specify a few more parameters in your problem to figure that out. Because here I didn't mention what any of these were made of. I was just saying here's an object. So it's a very simplified picture of reality.
Okay. I don't see any more questions, so thank you very much.